Welcome to this workshop on meta-analysis. This video is one in a series, and I recommend this one if you plan to work with correlations. This video includes both a basic section and also an advanced section. I'll cover the following items: how to enter data, how to run the analysis, how to estimate the mean correlation or effect size, how to understand heterogeneity in effects, how to report the results, and how to create plots. I'll also cover the following topics: how to perform a subgroups analysis, how to perform a meta-regression, and how to assess the potential impact of publication bias. I'll be using the software Comprehensive Meta-Analysis, or CMA. Our website is metaanalysis.com. There, you can download a free trial of the software and the datasets used in this video. This example is based on data from a systematic review that was published by Headland et al. 2017 in the Campbell Library. The systematic review was intended to see if a child's language ability at a very young age could be used to predict their language skills at a later age. If it turned out that the prediction was accurate, that would mean that we could use early assessments to identify children who might benefit from early intervention. If you're interested in the specifics of this analysis, please don't rely on this video, but consult the original paper, which can be accessed via the Campbell Library. The systematic review included multiple analyses. Here, I'll be replicating the one that they called Analysis 4. In this case, the predictor is the child's rhyme awareness at the younger age, and it's being used to predict word recognition at a later age. The analysis includes 14 studies. Let's look at the data first in Excel. The file is called readinganalysis4.xls. There's a column here with the study names. There's a column here with the correlation between the two assessments. There's a column here with the sample size. And there are columns with data for various moderators, such as the age at each assessment. I want to copy this data into CMA. There are two ways that I can do this. The first way is to copy the data into CMA and then identify the function of each column. The second way is to set up the relevant columns in CMA and then copy in the data. I'll use the second method here. I'll start the program. I'll close this box and this one. I'll click Insert Column for study names, and the program inserts this column. I'll click Insert Column for effect size data. The program opens this wizard. CMA will accept data in many formats, so I need to tell the program which format I want to use. I also have the option of entering data for some studies in one format, for other studies in a second format, and so on. At the bottom, I choose Show All 100 Formats, and I click Next. This button is the option that will allow me to compare two groups or to work with correlations. I choose that, and I click Next. On this frame, I choose Correlation. Since we already have the correlation, I choose Computed Effect Sizes. And then I choose Correlation and Sample Size. At this point, the Finish button lights up, and I click Finish. The program has now created a set of columns to hold the data. These are labeled Correlation, Sample Size, and Effect Direction. I could enter the data directly into CMA, or I can copy it from Excel. Let's return to Excel. I'm going to copy the data in two parts. First, I'll highlight the cells in these columns. I'll click Control-C to copy. I'll return to CMA. I'll click in the first cell over here, and I'll click Control-V to paste. I'll return to Excel. I'll highlight these cells and press Control-C to copy. I'll return to CMA. I'll click in this cell and press Control-V to paste. I still need to enter a value for the effect direction. I'll click in this cell. I'll select Auto, and I'll copy that to all the other rows. When I use Auto, the program will take the sign of the correlation that I entered here and keep it. In other words, a positive correlation is positive, and a negative correlation is negative. In our analysis, this works for all the studies because they all used scales where a high score was good. However, suppose that most of the studies used scales where a high score was good, but a few studies used a scale for the second assessment where a high score was bad. For example, rather than recording the score, they recorded the time needed to respond. If this had happened, then on most studies, a positive correlation would mean that the prediction worked, but on some studies, a negative correlation would mean that the prediction worked. In that case, we would need to use positive or negative rather than auto. In any study where a good score at time 1 was correlated with a good score at time 2, we would code that study as positive. And in any study where a good score at time 1 was correlated with a poor score at time 2, we would code that study as negative. This means that all studies which worked as expected would have a positive correlation, and all studies which went against our expectation would have a negative correlation. And this refers to any correlation that's not zero. It has nothing to do with statistical significance. By default, the program is displaying two effect size indices. This is the correlation, and this is the Fisher's z-score. When we run an analysis on correlations, we actually transform correlations into a metric called Fisher's z. We run the analysis in that metric, and then convert the numbers back to correlations for the display. All of this is automatic, and you never need to actually look at the z-score. It's there for people who want to have access to it. The program is displaying the error variance for each index and also the standard error for each index. If I wanted to modify any of this, I would right-click on the yellow columns, and I click the option to customize the display. The program opens this wizard. At the bottom, I can check whether or not I want to show the standard error and whether or not I want to show the variance. I can also check which indices I'd like to display. And then I click OK. These columns will serve as moderators. I'll come back later and explain what they are. Now I only want to name them. I double-click in this cell. I enter the name time 1. This column is time 2. This column is split. Now I can remove the first two rows. I'll highlight those rows and then select Edit, Delete Row. This would be a good time to save the file. I'll click the Save icon and give the file a name. In this analysis, all studies reported the data in the same format. What would I do if some studies reported data in another format? For example, suppose that this study had reported the correlation and its standard error, but not the sample size. I would click Insert Column for effect size data. I would click Correlation and Standard Error, and finish. Now, the program has created a set of columns for this data. I'll create a study called A. I'll enter the correlation as 0.62, the standard error as 0.068, and the direction as auto. Notice that the program's computed all the values here and here, which match what we saw before when we entered the correlation and sample size. When I run the analysis, the program will be working with the values in the yellow columns, and it doesn't matter what format we used to enter the data. I can switch back and forth between the formats just by clicking on any row or by selecting a tab at the bottom of the screen. I don't want to keep this fictional study, so I'll reopen the file that I saved a moment ago. To see recent files, I click this button, and then I double-click on the file that I just saved. The program asks if I want to save the current file before opening a new one, and I select No. Before I leave this screen, let me point out one more thing. If I wanted to see the formula that was used to compute the effect size, I would double-click on the yellow column that shows the effect size. The program shows the formula that was used, and then shows how the formula was applied to that study by plugging in the data for that specific row. Now let's run the analysis. I click Run Analysis. Here, I can select an effect size index. I'll be using the correlation. At the bottom of this screen, I can choose either the fixed effect model or the random effects model. I choose the random effects model for 3 reasons. First, it allows me to take account of the study-to-study variance when assigning weights to each study. Second, it allows me to assess the dispersion in effect size across studies. Third, this model will allow me to generalize from the studies in the analysis to the universe of comparable studies, which is what I intend to do. Next, I'd like to set the scale for the forest plot. I right-click on the plot, I select Scale, and I set the scale to -1 to +1. In this case, the studies are already sorted by effect size, but if they weren't, I would do that now so that I could get a general sense of how widely the effect size varies across studies. To do that, I would right-click on the column labeled Correlation and click Sort from Low to High. I get the sense that the effect size in most studies falls in the range of around 0.15 to 0.40, but there are a few studies with effect sizes outside that range. In any event, this is only intended to give me a general sense of the dispersion. We'll compute the actual dispersion momentarily. These columns show the statistics in numbers, and these are also plotted here. Since we're dealing with a correlation, the null value is 0. In this analysis, anything to the right of 0 indicates that the prediction worked as expected, and anything to the left of 0 indicates that the prediction was in the reverse direction. Each row displays data for one study, and there are 2 rows for the summary effect, here and here. To understand what these rows tell us, let me take a step back and explain the goals of a random effects analysis. When we perform a random effects analysis, we assume that there is a universe of potential studies that we care about. In this case, it might be all studies that have been performed or could be performed to study the correlation between these 2 assessments. I'll refer to this as the universe of comparable studies, or simply the universe. We assume that our 14 studies are a random sample from that universe, and so we can use these studies to make an inference to that universe. Our analysis has 3 goals. The first goal is to report the mean effect size in this universe. The second goal is to report how widely the true effect size varies. And the third goal is to identify factors that are associated with the magnitude of the effect. With that in mind, let's have a look at the analysis. This line gives me the mean correlation. The mean correlation is estimated as 0.319. The confidence interval is 0.237 to 0.396. That tells me that in the universe of comparable populations, the true mean probably falls in this interval. If we wanted to test the null hypothesis, that in the universe of comparable populations, the mean correlation is 0, the z-value for that test is 7.31, with the corresponding p-value of less than 0.001. We see that here, and we also see it here in that the confidence interval excludes 0. We would reject the null hypothesis that the mean correlation is 0 and conclude that, on average, the prediction works in the expected direction. Next, we want to report how widely the correlation varies across studies. To be clear, we do not want to simply report the lowest and highest correlations that we see here. If we did that, we would be basing our results on 2 studies and ignoring the information in the other 12. Rather, we want to use the dispersion and effects across all 14 studies to estimate how the correlations are distributed in the universe that we care about. To compute the actual amount of dispersion, we do something similar to what we would do in a primary study. We compute the standard deviation of true effects, and then we compute an interval based on the mean plus or minus 2 standard deviations. If we can assume that the effects are normally distributed in the relevant units, we would expect that the true effect size in 95% of all comparable populations will fall in that interval. When we do that, we get a statistic called the prediction interval, which is roughly 0.02 to 0.56. The interval is displayed here and also here. In 95% of all studies comparable to those in the analysis, the true effect size is expected to fall roughly in this interval. Why is this called a prediction interval? Well, suppose someone was thinking of using this method to predict performance in a population of children, and they asked me how well the prediction will work for this population. I would predict that the effect would fall somewhere between here, and I would be correct for some 95% of all populations. I should also address 2 common misconceptions. Some researchers think that the confidence interval tells us something about the dispersion in effects. For example, they might think that the effect size in individual studies ranges from here to here. And this is absolutely wrong. The confidence interval is an index of precision, not an index of dispersion. It tells us how precisely we've estimated the mean. It says nothing about how widely the effect size varies. A second common mistake is that people think that the I-squared statistic tells us how much the effect size varies. While this is a very common mistake, it's still a mistake. The I-squared statistic does not tell us how much the effect size varies. I discussed this in other videos and papers, but for now, I'll simply make the following point. In this analysis, I-squared is 67%. On that basis, how much does the effect size vary? The answer is there is no way to know. The I-squared statistic simply does not provide that information. To recap, these 2 lines address 2 distinct issues. This line deals with the average effect. The average effect falls someplace between here and here, while this line deals with the dispersion in effects. In any single population, the true effect size could be as low as this or as high as this. I can also create a high-resolution version of this plot. I'll show later how to create that plot, but right now I want to show one thing. These 2 rows are the same as the ones we saw a moment ago. This row displays the mean effect size and its confidence interval. Here, the confidence interval is displayed using a horizontal line, as it was in the prior plot, and we can also display it using a diamond, which is a common convention. However, whether we use a line or a diamond, the meaning is the same. The line or diamond represents the confidence interval. It tells us how precisely we've estimated the mean. It says nothing about the dispersion and effects. For dispersion, we turn to this row, which displays the prediction interval. In any single population, the true effect size will usually fall between here and here. CMA can also create a second plot, which takes the information in these two rows and presents it in a more intuitive format. If I click this button, the program generates this plot and these captions. This caption corresponds to this line. It reads, the mean effect size is 0.32, with a 95% confidence interval of 0.24 to 0.40. This caption corresponds to this line. It reads, the true effect size in 95% of all comparable populations falls in the interval 0.02 to 0.56. The prediction interval, 0.02 to 0.56, reflects the endpoints of this distribution. This is a useful way of summarizing the plot, but when it's possible to display the entire plot, we should do so, since it provides a more nuanced look at the distribution. The prediction interval told us that there were some populations where the effect was as low as 0.02 and others where it was as high as 0.56. The plot gives us a more detailed view. For example, I can see that in most populations, the effect falls somewhere between here and here. In only a relatively small number of populations does the effect fall in this range or in this one. Then I can edit the labels, and I can send this to Word or to PowerPoint. To see additional statistics, I'll click Next Table. This screen is divided into two parts. The left side of the screen deals with the mean effect size. The right side of the screen deals with heterogeneity. I'm going to use the statistics for the random effects model, and these are the same statistics that we saw on the prior screen. Here are the mean and its confidence interval. Here are the z-value and the p-value. Then let's look at the heterogeneity in effects. For heterogeneity, some of the statistics are presented on this row, and some are presented on this row, but they all apply to the random effects model. Here we have the q-value, along with its degrees of freedom and p-value. Here we have tau and tau squared. Here we have the I-squared statistic. And here we have the prediction interval. If you'd like to learn about these statistics, I have a paper that you can download for free on our website. Now I'll only make the following point. Each of these statistics addresses a specific question. We need to be clear about what question we intend to ask, and then we need to apply the appropriate statistic. One question we can ask is, does the true effect size vary at all across studies? For that, we turn to the q-value along with its degrees of freedom and p-value. If the p-value is less than the criterion alpha, we conclude that the true effect size does vary across studies. The criterion alpha for testing heterogeneity is sometimes set at 0.1 rather than 0.05, so any p-value under 0.1 would be considered statistically significant. In any event, the p-value here is less than 0.001, and so we conclude that the effect size does vary. In other words, the correlation is greater in some studies than in others. It seems to me that I can assume that this is true, and so I don't think that this test is informative, but almost everybody reports it. The second question we can ask is the following. What is the standard deviation of true effects, or what is the variance of true effects? These values are in Fisher's z-units, and they're given by tau and tau squared. A third question we can ask is the following. The dispersion that we see in the forest plot is partly due to variance in true effects and partly due to sampling error. So we can ask what proportion is due to variance in the true effects. That question is addressed by the I-squared statistic. In this case, I-squared is 67%. That tells us that 67% of the variance that we see reflects variance in true effects, while the other 33% is simply sampling error. Critically, 67% is a proportion, not an absolute amount. It does not tell us how much variance there is. The fourth question we can ask is the following. What is the range of true effects? Or, if I were to pick one population at random from the universe of comparable populations, what would the true correlation be in that population? That question is addressed by the prediction interval. In roughly 95% of all populations, the true correlation falls between 0.02 and 0.56. In practice, papers typically report the Q value along with its p-value, and they report tau squared and I squared. A common mistake in papers that report a meta-analysis is that these statistics, especially I squared, are then interpreted as telling us how much the effect size varies. However, that is incorrect. The I squared statistic does not tell us how much the effect size varies. That question is addressed by tau, or more intuitively by the prediction interval. There is one very important caveat to all of this. In order to estimate heterogeneity reliably, we need a minimum number of studies in the analysis. The number of studies needed will vary based on several factors. However, we might use 10 as a useful minimum to provide a sense of scale. When there is variation in the effect size, and there are less than 10 studies in the analysis, we cannot have confidence that any of the statistics related to heterogeneity will be reliable. And this includes I squared and tau squared, as well as the prediction interval. Next, I'd like to discuss how we would report the results. CMA will actually create a report that summarizes all of this data and can serve as a template for reporting. I simply click Report, and the program opens this screen, which reads as follows. Overview. The analysis is based on 14 studies. The effect size index is the correlation. Statistical model. The random effects model was employed for the analysis. The studies in the analysis are assumed to be a random sample from a universe of potential studies, and this analysis will be used to make an inference to that universe. What is the mean effect size? The mean effect size is 0.319 with a 95% confidence interval of 0.237 to 0.396. The mean effect size in the universe of comparable studies could fall anywhere in this interval. The z-value tests the null hypothesis that the mean effect size is 0. The z-value is 7.311 with a p-value of less than 0.001. Using a criterion alpha of 0.05, we reject the null hypothesis and conclude that in the universe of populations comparable to those in the analysis, the mean effect size is not precisely 0. The Q-test for heterogeneity. The Q-statistic provides a test of the null hypothesis that all studies in the analysis share a common effect size. If all studies shared the same true effect size, the expected value of Q would be equal to the degrees of freedom, which is the number of studies minus 1. The Q value is 39.251 with 13 degrees of freedom and a p-value of less than 0.001. So using a criterion alpha of 0.1, we can reject the null hypothesis that the true effect size is the same in all these studies. The I-squared statistic. The I-squared statistic is 67%, which tells us that some 67% of the variance in observed effects reflects variance in true effects rather than sampling error. Tau squared and tau. Tau squared, the variance of true effect sizes is 0.018 in Fisher's Z units, and tau, the standard deviation of true effect sizes, is 0.134 in Fisher's Z units. The prediction interval. If we assume that the true effects are normally distributed in Fisher's Z units, we can estimate that the prediction interval is 0.022 to 0.564. The true effect size in 95% of all comparable populations falls in this interval. Please note that my intention here is not to have the program write the report. I'm simply trying to ensure that the statistics are interpreted properly. Along those lines, there's also an option to annotate this report and provide additional information. For example, if I click that option, the section on the statistical model would read as follows. Statistical model. The random effects model was employed for the analysis. The studies in the analysis are assumed to be a random sample from a universe of potential studies, and this analysis will be used to make an inference to that universe. And then the program adds notes on the statistical model. This model applies when there is a universe of populations that we care about, and we can assume that the studies in the analysis are a random sample of those populations. The results of our analysis will be generalized to that universe. In general, when the studies in the analysis are pulled from the literature, this is the model we should be using. This is the model that allows us to generalize to the universe of comparable studies, which is typically what we intend to do. At the same time, we need to be aware of the limitations of this model when employed in this way. In particular, for the model to work properly, we need a sufficient number of studies to yield a reliable estimate of tau squared, the between-study variance. Additionally, while we can say that the results apply to the universe of comparable studies, it may not be clear what that universe includes. And finally, the program inserts citations and references. And the report can be exported to other programs, such as Word. Next, I'd like to create a high-resolution version of the forest plot. To do that, I'll click High Resolution Plot. Here, I'll click Reset All. This is the basic plot, but I can edit any element on the plot. For example, I'll right-click on the title and edit the title to Predicting Word Recognition. I want to modify the symbol for the prediction interval. I right-click anywhere on the plot. I click Study and Summary Symbols. I click the tab for Prediction Intervals. I click here to increase the line width, and I click here to add a cap at either end. Next, I can set the color for this symbol. The two sides of the plot are labeled favors A and favors B. I'll right-click on favors A. I enter the labels negative and positive, and I can change the font size. The footer reads meta-analysis. I'll right-click on the footer and edit it to read random effects. I'd like to send this to PowerPoint. I click File, Export to PowerPoint. The program opens PowerPoint and inserts the plot. In PowerPoint, I can display this full screen. I'll return to CMA. Back in CMA, I can choose colors for slides. I can modify any or all of the colors on this slide. I'll edit the color for the title. and I'll edit the color for the line under the title. And then send it back to PowerPoint again. If I wanted to, I could send this directly to Word, or I could save it as a file and then import it into any program. So that's it for the basic analysis. When we analyze a primary study, we typically perform a sensitivity analysis. This means that we might perform a series of analyses to ensure that the results are robust. For example, we might want to ensure that the results were not overly influenced by any one outlier. We can do something similar in a meta-analysis. Here, I'll outline some procedures that we might want to include as part of a sensitivity analysis. One issue we might want to explore is how much of an impact each study had on the analysis. Recall that the summary effect size is a weighted mean of the individual effect sizes. We might want to see how much weight was assigned to each study. If I click this button, I can display a column with the relative weight assigned to each study. Initially, these bars are on a scale of 0 to 100. But to see the weights more clearly, I can right-click here, and then I choose Scale Relative to Maximum. This changes the scale so that differences among the weights are now easier to see. Additionally, I can sort by relative weight. I right-click on the weights. I select Sort from High to Low. We can see that no study gets more than around 10% of the weight. And this tells me that I don't need to be concerned that any one study dominated the analysis. I can also see that almost every study gets at least 4% of the weight, and this tells me that most of the studies played a non-trivial role in the estimates of the mean effect size and the heterogeneity. Another type of sensitivity analysis is to ensure that the results are robust in the sense that the basic conclusions are not dependent on any one study. To look at that, we could run the analysis with only the first study removed, then with only the second study removed, and so on. CMA actually allows us to perform this kind of sensitivity analysis with one click. First, I'll return to the data entry screen and sort the studies by effect size. Then I'll run the analysis again. Let's focus on Cronin, since this is the study with the highest effect size, which is 0.62. At the bottom of the screen, I have a tab for basic stats, and I have a tab labeled One Study Removed. I'll click on the tab for One Study Removed. Now, the row labeled Cronin does not show the results for Cronin. Rather, the row labeled Cronin shows the results for an analysis based on all studies except for Cronin. On the row labeled Cronin, the effect size is 0.29. And this is what we would see on the yellow line if we ran an analysis using the other 13 studies. Recall that the mean effect size with all 14 studies was 0.32. Now we know that without this study, the mean effect size would have been around 0.29. So this study pulled the mean effect to the right from 0.29 to 0.32. From a substantive perspective, these two values are basically the same. So the essential conclusions would remain the same if we removed this study from the analysis. As I scan the set of analyses, I see that regardless of which study I remove, the basic conclusions remain unchanged. This row continues to show the original results, and if I compare each row to this row, I see that the mean effect size never moves to the left nor to the right by enough to change the substantive implications of the finding. I'm not a fan of p-values, but if we are concerned about a test of the null hypothesis, notice that the p-value is always less than 0.001 with any one study removed. So this plot allows me to report that the results are robust in the sense that the conclusions remain essentially the same with any one study removed. Now I'll click Basic Stats and return to the standard analysis screen. Next, I'd like to perform an analysis of publication bias. The logic of publication bias is discussed at length in another module, so here I'll focus on the results. I'll click Analysis, Publication Bias. The program displays what is traditionally known as a funnel plot. Large studies are plotted at the top, and the small studies are plotted at the bottom. To be clear, there's no specific demarcation between large and small studies. The areas that I've indicated by these arrows are somewhat arbitrary. This line corresponds to the mean effect size. The diamond corresponds to the mean effect size and its confidence interval. Initially, the mean and confidence interval are based on the fixed effect model. Since we're working with the random effects model, I'll select that here. And the mean and confidence interval now match those that we saw on the main analysis screen. On the main screen, the anchor was at 0, and here the anchor is at the mean effect size. And this makes it easier to see how studies vary about the mean. Notice that the scale here is in Fisher's Z units, and so the mean and confidence interval are in Fisher's Z units. Most models of publication bias assume that most of the large studies have been published. That's because large studies tend to be statistically significant even when the effect size is relatively small. Additionally, even when large studies are not statistically significant, there are various incentives to publish them. And therefore we expect that essentially all of the large studies will be published. And, based on the laws of statistics, we expect them to be evenly distributed on either side of the mean. By contrast, we expect that only some of the smaller studies have been published. Specifically, small studies that reported large effects would tend to be statistically significant and likely to be published, while small studies that reported smaller effects might not be statistically significant and might not have been published. So, if there's no publication bias, we would expect to see large studies evenly distributed on both sides of the mean, and we would also expect small studies to be evenly distributed on both sides of the mean. On the other hand, if there is publication bias among the small studies, that would mean that there are some studies missing over here. Why on the left rather than the right? Well, because non-significant studies will fall closer to the null value, which in this case is to the left of the mean. So that's where I would expect studies to be missing. I see no evidence of that. If anything, the opposite seems to be true. That is, there seem to be more studies to the left of the mean than to the right of the mean. In any event, let's look at the actual numbers. I click View, Trim, and Fill. I click Look for Missing Studies to the left of the mean. There's an option here to use either the fixed effect model or the random effects model to look for the missing studies. While we'll be using the random effects model to conduct the actual analysis, there is still a convention to use the fixed effect model to look for the missing studies. If I wanted to follow that convention, I would make that selection here. Then I click Funnel Plot. Finally, I click Plot Observed and Imputed. If there had been evidence that studies were missing to the left of the mean, the trim and fill procedure would impute those studies and add them to the analysis. In this case, the procedure determines that there's no evidence of an imbalance, and so no studies are added. At the bottom, we now have two diamonds. Based on the original studies, the mean effect size and its confidence interval would be here. Based on the original studies plus the imputed studies, the mean effect size and its confidence interval would be here. In this analysis, there's no evidence that any studies are missing, and so the two diamonds are identical to each other. To see the actual values corresponding to these diamonds, I can again click View, Trim, and Fill. As I mentioned before, there's a convention to use the fixed effect model for determining how many studies might be missing. Even if we adopt that convention, when we rerun the analysis with the inclusion of these studies, we still want to apply the random effects model. This section shows the results for the random effects model, and it's the one that we want to use. This row shows the results based on the 14 actual studies and corresponds to the open diamond, while this row shows the results based on the 14 actual studies plus the 0 imputed studies and corresponds to the closed diamond. In both cases, the mean, which is presented in correlation units, is around 0.32. While this analysis ends here, since there's no evidence of any missing studies, I should explain how I would interpret these numbers if the procedure had added some studies. Suppose that the new value, rather than 0.32, was 0.27. I would say that if there is bias due to missing studies, the basic conclusions remain unchanged. Since from a substantive point of view, a correlation of 0.27 is not that much different than a correlation of 0.32. On the other hand, suppose that the new value was 0.15 rather than 0.32. In that case, I would say that if there is bias due to missing studies, our initial estimate may be based on a biased subset of all the studies that had been performed, and that the estimate of 0.32 might exaggerate the true effect in the universe of relevant studies. Notice that I said if there is bias due to missing studies, because that might not be the case. The trim and fill procedure, like most procedures to assess publication bias, looks to see if the effect size for the small studies tends to be larger than the effect size for the large studies. If we find few studies here and more studies here, we might assume that these studies actually exist but are missing from the analysis. However, that might not be the case. It's entirely possible that small studies do actually tend to show larger effects for perfectly legitimate reasons. For example, it's possible that the small studies were performed by people who have been carefully trained in the use of the rating scales, while larger studies were performed by people with less training. Or it's possible that smaller studies enrolled older children, and that the correlation between the two assessments was actually higher for the older children. In any event, in our analysis, these issues are all moot, since there's no evidence that any studies are missing. CMA is able to run various other tests for publication bias. I won't discuss them here, but simply mention that these include the fail-safe N, the rank correlation test, and Egger's regression test. Additionally, within the publication bias module, if you click View Report, the program will generate a detailed report that discusses all of these analyses and how to interpret them. There are two procedures that we employ to identify factors that are associated with the size of the effect. These are subgroup analysis and meta-regression. Here, I'll show how these procedures can be applied in this case. Let's return to the data entry screen. The columns over here are for variables that might be related to the effect size. This is time 1, which is the child's age in months of the first assessment. We need to tell the program that this is a moderator variable. I double-click on the title. The column function is a moderator, and we also need to specify the data type. The options here are categorical, integer, or decimal. Since most of these are integers, and I don't care about the decimal, I'm going to select integer. Time 2 is the child's age in months of the second assessment. The column function is a moderator. the data type is integer. The column called split is based on time too, but rather than the age in months, we coded each study's age as 8 years or less versus 9 years or more. The column function is a moderator, and this time the data type is categorical since each study is assigned to a category. Now we can return to the analysis screen. I click Run Analysis. I click Random Effects, and I click Computational Options Group By. The only moderator displayed here is split because this was defined as categorical. The other moderators were either integer or decimal. I select split, I add a check mark to each of these options, and I click OK. Finally, I'll right-click on the correlation and sort from low to high. As always, there are two summary rows. The confidence interval addresses the mean correlation, while the prediction interval addresses the dispersion in correlations. Initially, I want to focus on the mean correlation rather than the dispersion, so I will deselect this button to hide the prediction intervals. These are the studies where the second evaluation was at age 8 or younger. The mean correlation is 0.23. These are the studies where the second evaluation was age 9 or older, and the mean correlation is 0.40. To get a better sense of the difference between the two, I can hide the individual studies and display only the summary rows. To hide the individual studies, I deselect this button. For studies where the second evaluation was at a younger age, the mean correlation is 0.23. For studies where the second evaluation was at an older age, the mean correlation is 0.40. I think it's clear that the difference is of substantive importance. Additionally, I can see that there's no overlap between the two confidence intervals, so I expect that the difference in means will be statistically significant. We'll look at that in a moment. I'll click this button again to redisplay the individual studies. Next, I want to see if this difference is statistically significant. I click Next Table. This section is labeled Mixed Effects Analysis, and this is the section I want to use. I'll explain later what it means. The mean effect sizes are the same ones that we saw a moment ago. For the 9 studies in the first set, the mean correlation is 0.23. For the 5 studies in the second set, the mean correlation is 0.44. To compare this mean versus this one, I can use a Q-test. The Q value is 12.786 with 1 degree of freedom and a p-value of less than 0.001. I would reject the null hypothesis that the mean correlation is the same here and here. I would conclude that the correlation is higher here. So to recap, we've concluded that the difference between this correlation and this one is statistically significant. I wanted to start with that conclusion, but in running these computations, I made a series of decisions. I need to discuss what those decisions were and why I made them. We also need to discuss what conclusions we can draw from the analysis, and equally important, what conclusions we cannot draw from the analysis. The first issue I want to discuss is the choice of a statistical model. As always, at the bottom of the screen, we can select either the fixed effect model or the random effects model. I selected the random effects model, and let's be clear about what that means. When we were performing a simple analysis without subgroups, the difference between fixed effect and random effects is as follows. We used the fixed effect model if we believed that all studies were based on the same population and were identical to each other in all material respects. For example, the fixed effect model would apply if the true effect size for all studies fell directly on this line, and the observed effects deviated from the line only because of sampling error. That means that the true effect size is the same in all studies because all studies are based on the same population, and the results would apply to that population only and could not be generalized to any other populations. By contrast, we would use the random effects model if we believed that studies were based on different populations or varied from each other in meaningful ways. For example, the true effect size for the various studies might fall along this line. The true effect size varies from study to study because each study is based on a unique population. And the results would apply to the universe of comparable populations. As I explained earlier, on that basis, the random effects model is almost always the one that we want to use. The same idea applies here, except that now we apply this criteria within subgroups. And again, on that basis, the random effects model is almost always the one that we want to use. For example, consider the studies in this subgroup. If we believed that these studies were all based on the same population and were identical to each other in all material respects, we would use the fixed effect model to estimate the common effect size here, and that effect size would apply to that one population only. However, that's clearly not the case. While these studies are similar to each other, in the sense that they all conducted the second assessment when the children were 8 years or younger, they are not based on the same population, and they do vary from each other in many important ways. Therefore, we apply the random effects model here, and this allows us to generalize to the universe of comparable studies. Similarly, if we believed that all of these studies were based on the same population and were identical to each other in all material respects, we would use the fixed effect model to estimate the common effect size here, and that effect size would apply only to that one population. However, again, that is clearly not the case. While these studies are similar to each other in the sense that they all conducted the second evaluation when the children were 9 or older, they are not based on the same population, and they do vary from each other in many important ways. Therefore, again, we apply the random effects model. And this also allows us to generalize the results to the universe of comparable studies. In any meta-analysis, we need to compute tau-squared, the variation in true effect sizes across studies. In a simple analysis, when we have only one set of studies, we compute tau-squared across all those studies. But when we have subgroups, we must compute tau-squared within the subgroups. For the first set of studies, tau-squared is estimated as 0.0. For the second set of studies, tau-squared is estimated as 0.02. At this point, we have two options for how to use these estimates. We can pool the two estimates. If we do that, we get a pooled estimate of 0.005. And then we can use that pooled estimate for both subgroups. Or we can apply each estimate to the corresponding subgroup. Since tau-squared plays a role in the weights assigned to each study, the decision that we make about pooling will affect the values that we see here and here. The first option is to pool the two values to get a common estimate, and then apply that estimate to both subgroups. And that yields the numbers that I see here. This correlation is 0.23 with this confidence interval. This correlation is 0.44 with this confidence interval. The second option is not to pool the two estimates of tau-squared. Rather, we would use the value of 0.00 to compute the statistics for this set of studies, and we would use the value of 0.02 to compute the statistics for this set of studies. And that would yield the numbers that I see here. This correlation is 0.22 with this confidence interval, and this correlation is 0.45 with this confidence interval. In almost all cases, I want to pool the estimates. Why do I choose to pool the estimates? The reason is that an estimate of tau squared based on a small number of studies is not reliable. The estimate here is based on 9 studies and is not very reliable. The estimate here is based on 5 studies and is not reliable at all. So, if we used the 2 estimates without pooling, the estimates would be poor. By contrast, if we pool them, we have an estimate based on 14 studies, which is better. Obviously, when we pool the 2 values, we might be losing information. If the variance in effects for this kind of study is actually greater than the variance in effects for this kind of study, we lose that information when we pool. However, the amount of error that we introduce by pooling is likely to be much less than the amount of error we introduce by estimating tau squared based on 5 studies. And so I choose the option to pool. How do I specify which option I want to use? I click Computational Options, Mixed, and Random Effects Options. In the top part of this panel, I choose the option to pool the values. If you'd like to see the actual value of tau squared, click Next Table. The value of tau squared is displayed here. If I selected the option to use separate estimates of tau squared for the first subgroup is 0.00, and tau squared for the second subgroup is 0.02. And these are the statistics that we would get for each group. On the other hand, if I select the option to pool the estimates, tau squared for each subgroup is 0.005, and these are the statistics that we would get for each group. And that's the option that I would use in this analysis. In this example, the 2 approaches yield similar estimates of the mean, but in many cases, the estimates would differ substantially. So the choice to use one approach or the other can be very important. To this point, I've explained why we want to choose a random effects analysis. Now, I need to discuss why this is called a mixed effects analysis rather than a random effects analysis. The reason is that we need to choose a statistical model at 2 levels. Within subgroups, we're using random effects. That is, we use a random effects model to synthesize the data from these studies and yield these numbers, and we use a random effects model to synthesize the data from these studies and yield these numbers. At the same time, however, we're using a fixed effects model to select the 2 subgroups. And those are the subgroups which conduct the second evaluation at a younger age or at an older age. The 2 subgroups are fixed. The word fixed here does not mean that the 2 subgroups are the same, since obviously they're not. Rather, they're fixed in the sense that they've been selected or identified. In other words, we care about these specific subgroups only. We want to know the mean effect here and here. We will not be generalizing from these 2 subgroups to other subgroups. For example, subgroups where the children were 13 years old. Such subgroups don't exist. To specify that we'll be using fixed effects for the subgroups, I click Computational Options, Mixed, and Random Effects Analysis. This selection is made on the bottom part of this panel. I select the option to combine subgroups using the fixed effects model. To recap, we'll be using the fixed effects model to identify the specific subgroups we care about. We set that here. And we'll be using the random effects model within subgroups. We set that here. Since we're using fixed effects at one level and random effects at the other, this is called a mixed effects model. And these are almost always the options that you'll want to use. Now, let's return to the key finding. The difference between this mean and this one is statistically significant. What does that tell us? The answer is probably not what you'd expect. I am able to say that the effect size here was greater than the effect size here. However, I cannot say that this is due to the fact that these studies did the second assessment when the kids were younger, and these studies did the second assessment when the kids were older. Let me say that again. I can say that the effect size is higher here than here, and that the difference is statistically significant, but I cannot say that this difference is due to the age at the second assessment. That might sound counterintuitive, so let me unpack this. As we saw a moment ago, the difference between this correlation and this one is statistically significant. So we can say that the correlation is higher in this type of study than in this type of study. But we cannot say that the age at the second assessment is the relevant difference between these studies and these. In other words, the difference that's responsible for the higher correlation that we see here. And the reason is that we did not use a random process to assign studies to perform the second assessment at a younger age or an older age. Therefore, there might be other variables that are confounded with age. For example, suppose that the studies which performed the second assessment at an older age also tended to perform the first assessment at an older age, and that it was the age at the initial assessment rather than the age at the later assessment that's responsible for the higher correlation that we see here. We chose to call these groups younger versus older at the second assessment, but it's possible that it would be correct and more relevant to call them younger versus older at the initial assessment. Or it's possible that studies which performed the second assessment with younger children tended to use one technique to measure word recognition, while those which performed the second assessment with older children tended to use a different technique to measure word recognition. And it's possible that the technique employed with the older children was responsible for the higher correlations. Again, we chose to call these younger versus older at the second assessment, but it's possible that a more appropriate label would have been Technique A versus Technique B, and so on for other potential confounds. The key point is that the difference between subgroups is almost always observational rather than causal. So we can say that the correlation was higher in studies that performed the second evaluation when the children were older, but we cannot say that this is because the children were older. It might be due to that, but it could also be due to some other factor which is confounded with the time of the second assessment. As we'll see later, we might be able to use meta-regression to shed some light on this question. This is the mean correlation for studies that performed the second assessment when the children were younger. This is the mean correlation for studies that performed the second assessment when the children were older. And this is the mean correlation across all studies. We need to ask if it makes sense to report this value. In some cases, it will make sense to report the value, and in some cases, it will not. But it's important to understand what this value represents. The mean here is a weighted mean of this one and this one. Since this subgroup has more studies than this one, it will tend to carry more weight in computing the overall mean. The mean effect size here can be thought of as the mean effect size in a universe where roughly 2/3 of the studies performed the second assessment with younger children and roughly 1/3 performed the second assessment with older children. I'm not sure that this is a universe I would care about, and so I might choose to remove the line with the overall effect size. To do that, I deselect this button, and the overall effect size is now hidden. On the other hand, if the mean in all subgroups had been comparable, I might have elected to display the overall mean. When we first looked at subgroups, the screen looked like this. For each subgroup, the program displayed two lines. This line reflects the mean for this subgroup. This line reflects the dispersion of effects for this subgroup. This line reflects the mean for this subgroup, and this line reflects the dispersion in effects for this subgroup. I said that I wanted to focus initially on the difference in means, and so I would hide the dispersion and display only the means. The reason that I started by focusing on the means is that this is what everyone does when they compare subgroups. It turned out that this mean was 0.44, while this one was 0.23. We did a test of significance, which told us that the difference was statistically significant. And that means that the difference between the average effect here and the average effect here is probably not zero. While all papers that look at subgroups start by comparing means, most papers also stop after comparing means. That is, they report that the difference in means is or is not statistically significant. It seems to me that this is a mistake because it does not tell us about the substantive implications of the difference. We know that the mean is higher here than here, but if we want to know how useful the intervention might be in either subgroup, it's not enough to know that this mean is higher. We also need to know what proportion of these studies will yield a useful correlation, and what proportion of these studies will yield a useful correlation. And to do that, we need to know what the distribution of effects looks like here and here. For that, we turn to the prediction intervals. The distribution of effects in the first subgroup looks like this, and in the second subgroup looks like this. Suppose we decide that correlations above 0.45 are potentially useful for identifying children at risk. In this subgroup, the assessment would never be useful. In this subgroup, the assessment might be useful in roughly half the cases. And that information directly addresses the question we care about, which is how useful is this assessment likely to be in each subgroup. The limitations that we discussed earlier when we spoke about means also apply here when we're talking about the distributions. This includes the fact that the difference between subgroups is observational and not causal. That is, we're calling these groups younger versus older at the second assessment. The difference between the two distributions might be due to this variable, but could also be due to another variable that's confounded with this one. There are two things that I can do with meta-regression that I cannot do with the subgroups analysis. The first is that regression allows me to use continuous covariates. When I use subgroups analysis, I can only work with categorical moderators. In fact, that's the reason I classified the studies into two groups, 8 or younger versus 9 or older. I could have also created more than two groups, but would always be limited by groupings. By contrast, when I use regression, I can use the actual age as a predictor. The second advantage to regression is that we can look at the impact of any covariate while controlling for other covariates. For example, in this analysis, we discovered that the correlation is higher when the second assessment was performed at an older age. That could be because performing the second assessment at an older age yields a higher correlation. But it's also possible that studies which performed the second assessment at an older age also performed the initial assessment at an older age, and that the age at the initial assessment, rather than the age at the second assessment, is the reason for the higher correlation that we see in these studies. We can use metaregression to address this question. Specifically, we can look at the relationship between time 2 and the correlation while holding time 1 constant. In other words, we can isolate the unique impact of time 2 on the magnitude of the correlation. An important caveat to all of these procedures is that we need to have sufficient data to run the analysis reliably. When we're using a subgroups analysis, I would hope to have at least 5 studies in each subgroup, and when we're using a metaregression, I would hope to have at least 10 studies for each covariate. These two requirements are actually the same, since 2 subgroups corresponds to 1 covariate. These are broad rules of thumb, but I'm hoping to impart a sense of scale. While it's technically possible to run a regression with 10 studies and many covariates, the results will not be informative. To perform a metaregression, we proceed as follows. First, I need to remove the subgrouping. I'll click Computational Options, Group By, Reset. And then I'll click Analysis, Metaregression 2. This frame shows all the moderators I had identified on the data entry screen. Note that this includes both continuous and categorical moderators, since both can be used in a metaregression. I'll click on Time 2. I'll click Add to Main Screen, and the program moves Time 2 from here to here. I add a check mark for Time 2, and then I click Run Regression. This table reports the statistics. I'll come back to this momentarily, but first I'd like to see a plot of the data, which will provide some context for understanding the statistics. I click Scatter Plot, and the program switches to this screen. The title is Regression of Fisher's Z on Time 2. The x-axis is Time 2. The scale goes from 60 to 160 months. The actual ages at Time 2 range from roughly 80 to 140 months. The y-axis is the correlation in Fisher's Z units. The scale goes from minus 0.20 to plus 1.40. The actual effects range roughly from 0.20 to 0.60. The regression line moves from the lower left to the upper right. As the age at Time 2 gets higher, the correlation gets higher. For studies where the age at Time 2 is 80 months, the predicted correlation in Fisher's Z is roughly 0.20. For studies where the age at Time 2 is 140 months, the predicted correlation in Fisher's Z units is roughly 0.60. The first thing we should address is the fact that these values are in Fisher's Z units. I'd like some sense of what they would be in correlation units. Let's return to the main results screen. This table gives me the relationship between Time 2 and the correlation when all other variables are held constant. In this case, the only variable in the equation is Time 2, and so this is simply the relationship between Time 2 and the effect size. As Time 2 increases by 1 month, the correlation in Fisher's Z units increases by 0.007. To make this more intuitive, I could multiply both of these values by 12. As Time 2 increases by 12 months or a year, the correlation in Fisher's Z units increases by around 0.08. Or I can multiply both of these values by 60 months, which is 5 years. As Time 2 increases by 60 months, the correlation in Z units increases by roughly 0.42. We can also test the null hypothesis that there's no relationship between time 2 and effect size. In other words, that the true coefficient is 0. The z-value for that test is 3.46, and the p-value is less than 0.001. If we're using a criterion alpha of 0.05, we would reject the null hypothesis that there's no relation between time 2 and effect size. Where the table at the top provides information for each covariate, with all other covariates held constant, this table provides information for the full set of covariates. Put another way, this asks if any of the covariates are able to explain any of the variance in effect size. In this case, since there's only one covariate in the analysis, this analysis is the same as this one. This analysis uses a Q value rather than a Z value. The Q value is 11.99 with 1 degree of freedom and a p-value of less than 0.001. Since there's only one covariate, this p-value is addressing the same null hypothesis as this one, and the two values are therefore the same. In fact, when there's only one covariate, the Q value is simply the square of the Z value. The part we just looked at addresses the question, did the covariates explain any of the variation in effects? By contrast, this part asks if the covariates explain all of the variation in effects. To explain what this part means, let's have another look at the plot. We have the regression line, and we have the individual studies. The null hypothesis being tested in the second part is that time 2 is able to explain all of the variation in effects. Put another way, the null hypothesis being tested is that the true effect size for all studies falls directly on the regression line. Of course, most of the observed effects fall some distance from the regression line, but the null hypothesis refers to the true effects rather than the observed effects. The null hypothesis is that the true effect size for this study is actually here, and the observed effect size is here only because of sampling error. Similarly, the true effect size for this study is actually here, and the observed effect size is here only because of sampling error, and so on for all the other studies. To test this null hypothesis, we use a Q value. The Q value is 19.545 with 12 degrees of freedom and a p-value of 0.07. By convention, we use a criterion alpha of 0.10 rather than 0.05 to test this null hypothesis. And since 0.07 is less than 0.10, we would reject this null hypothesis and conclude that time 2 does not explain all of the variation in effects. Taking these two elements together, we conclude that time 2 explains some of the variation in effect size, but not all of the variation in effect size. When we were working with a simple analysis, we discussed the Q test for heterogeneity. A significant Q value provided evidence that the true effect size was not identical in all studies. I said at the time that I don't think this test is informative, because when we're looking at studies of this kind that were pulled from the literature, we can assume that the true effect size varies. To suggest that the true correlation is identical in all these studies is simply not plausible. So there, rather than ask whether there was evidence of any dispersion in effects, I said that we should ask how much dispersion there was. The same idea applies here. The null hypothesis being tested here is that the true effect size for all studies falls directly on this regression line. It seems to me that it's simply not plausible to think that this is the case. So I'm going to assume that the true effects do vary around the regression line, and the question I'd like to ask is how much do they vary? For that, I turn to tau and tau squared. In the simple analysis, when we had no covariates, if we wanted to predict the effect size for any study, we would predict the mean. And there would have been a lot of error in that prediction. Specifically, the variance of true effects about the mean, tau squared, was 0.018. Now we're using time 2 and this regression line to predict the correlation. And the variance around this regression line is 0.0058. So by using time 2, we can reduce the error in prediction. 0.0058 over 0.0180 is 0.32. So the new error is only 32% as much as the initial error. 1.0 minus 32% is 68%. So using time 2 as a predictor allows us to explain 68% of the initial variance. And that's the meaning of this statistic. This is called the R-square analog, which is 68%. It tells us that the covariate is able to explain 68% of the variation in true effects. This statistic is called the R-square analog because it's analogous to the R-squared statistic that we use in multiple regression in primary studies. But it does differ from that statistic in some important ways, as I've explained elsewhere. So far, we know that time 2 is related to the magnitude of the correlation. This is a slightly different analysis than we performed earlier with subgroups, since now we use the actual age at time 2 rather than classifying studies into younger versus older. However, we still have not addressed the question of confounds. It's possible that the correlation here is higher because these studies performed the follow-up assessment at a later age, but it's also possible that these studies differed from these in some other ways. For example, it's possible that these studies also performed the initial assessment at a later age. And it's possible that the timing of the initial assessment, rather than the timing of the follow-up assessment, is responsible for the higher correlations that we see here. So, simply moving to regression does nothing to address the problem of confounds. However, we can address it by incorporating both time 1 and time 2 in the analysis. Before we do that, however, to get a better sense of the data, let's look at time 1 alone as a moderator. I'll click Modify Models. I'll click on time 1. I'll add it to the model. I'll move it up so that it will appear above time 2 in the table. This actually has no impact on the analysis, only on the display. First, I want to run an analysis with time 1 alone. So I'll add a check mark for time 1, and I'll remove the check mark for time 2. And now I'll click Run Regression. This screen shows the results in tabular form. As I did before, I want to look at the scatter plot to get some context. In this case, the regression line runs from upper left to lower right. When the first assessment was performed at 45 months, the correlation was around 0.55, but when it was performed at 80 months, the correlation was around 0.25. So if anything, an older age at the first assessment is related to a lower correlation. Overturn to the tables. The coefficient for this variable is minus 0.008, but the standard error is large, and the confidence interval includes 0. Equivalently, if we wanted to test the null hypothesis that the true coefficient is 0, the z-value would be minus 1.65, and the p-value would be 0.098. So this is not statistically significant. In other words, the relationship suggested by the regression line could be due entirely to sampling error. There's no evidence that age at the initial assessment is related to the magnitude of the correlation. As I mentioned earlier, regression offers two important advantages over a subgroups analysis. One is that it allows us to work with the continuous covariate. We just looked at that. The other is that it allows us to assess the impact of a covariate while controlling for other covariates. We established earlier that time 2 is related to the magnitude of the correlation. When the second assessment is performed later, it works better. But we were concerned that this could be due to a confound with time 1. We can use regression to isolate the impact of time 2 while controlling for time 1. I'll click Modify Models. I'll add a check mark for both time 1 and time 2, and I'll click Run Regression. As before, the coefficient for time 1 is negative, and the coefficient for time 2 is positive. They both happen to be 0.006. Now let's look at the plots. This is time 1. When we control for time 2, as time 1 goes from 45 to 80, the correlation drops by around 21 points. Now, I'll plot by time 2. To plot by time 2, I will click here and select time 2. When we control for time 1, as time 2 goes from 80 to 140, the correlation increases by around 36 points. Now let's return to the numbers. Remember that this table is now giving us the impact of each covariate with the other covariate held constant. The confidence interval for time 1 is relatively wide, and we cannot reject the null hypothesis that the true coefficient here is 0. By contrast, the confidence interval for time 2 is relatively narrow, and we can reject the null hypothesis that the true coefficient here is 0. The z-value for that test is 3.107, and the p-value is 0.002. To recap, it's clear that time 2 is related to the magnitude of the correlation, and it's also clear that this is not due to a confound with time 1. To really understand what's happening here, I would want to perform additional analyses. I would also like to explore the possibility of an interaction between time 1 and time 2. Unfortunately, with only 14 studies in the analysis, we cannot do this reliably. To this point, I've been using the z-distribution to compute the confidence intervals and p-values for the coefficient and for the overall effect. If I click Computational Options, I see that we're using the z-distribution, and this is also displayed here. However, it's generally a better idea to use the Knapp-Hartung-Siddig-Yankman adjustment. This adjustment yields a confidence interval and p-value that tends to be more accurate than the one we get using a z-distribution. I can click Computational Options Knapp-Hartung. Now, this table shows us the adjusted confidence interval, a t-value rather than a z-value, and an updated p-value. Similarly, this table shows us the f statistic rather than the q-value, and an updated p-value. This was intended as an overview of the meta-regression module. For a more complete discussion of meta-analysis, consider subscribing to our workshops, which are now available online. For more information, visit metaanalysisworkshops.com. And this is also where you can download a free PDF of our text, Common Mistakes in Meta-Analysis and How to Avoid Them. In this analysis, I used the software Comprehensive Meta-Analysis. For information about the software, please visit this website. My name is Michael Borenstein. This is my email, and please feel free to contact me with any questions or comments.